Circus, Afro circus, Afro circus, Afro boogie.
Come on, I said circuits, not circus. Come on.
What is a circuit? Well, a circuit is a complete and closed path around which a circulating electric current can flow. It provides electricity to all your appliances in your house and, well, this video.
Direct current is circuits in which the battery's potential difference is unchanging and all the currents in the circuit are constant. Alternating current is an electric current that reverses its direction many times a second at regular intervals, and it's typically used in power supplies.
Yo, so what do you think about what does the Physics Council think?
Electric current is defined as the rate at which charge flows through a surface. Despite referring to many different things, the word current is often used by itself instead of the longer, more formal electric current.
Wow, what an interesting concept right there.
Thank you.
This is Ohm's law. It relates the current to the potential difference between the ends of the conductor. Current equals change in voltage over resistance. This is a vital equation to solving the unknown variables in a circuit.
You told me vehicles IR.
Voltage, also known as electric potential difference, is measured in units of volts, or joules per coulomb, by a voltmeter. It is equal to the work done per unit of charge against a static electric field to move the charge between 2 points. Yeah. Resistance is the ratio of the voltage applied to the electric current which flows through it. If the resistance is constant over a considerable range of voltage, then Ohm's law, I equals V over R, can be used to solve for other components. Homie. Resistors limit the current by using circuit elements that, although they are conductors, have a resistance slightly larger than the wires themselves. Current, or I in Ohm's law, means the charge or the electrons flowing through the wires in a circuit. It is the rate at which the charge flows past a point on a circuit. It is measured in amperes, which is equal to quantity of the charge Q over time T. A battery is an electrochemical cell when two different metals in contact through an electrolyte, which is a liquid with free-moving ions. A set of connected cells is called a battery, and it serves as a power source for the circuits.
But this rabbit can tell George about physics.
Hey, Mr. Rabbit. How's it going?
According to the old
Don't eat me.
capacitor current is proportional to the time derivative of capacitor voltage. You ever cared? No? Anyways, another way of saying this is that to state that capacitors differentiate voltage with respect to time. Express this time derivative of voltage as a current. Suppose we had an oscilloscope capable of directly measuring current, or at least a current to voltage converter that we could attach to one of the probe inputs to allow direct measurement of current on each end. As such an instrument set up, we could directly plot capacitor voltage and capacitor current all together on the same display.
Thank you, Mr. Rabbit.
A series circuit is a closed circuit in which the current flows one path, as opposed to a parallel circuit where a circuit is divided into two or more paths. The current through each load is the same, and the total voltage across the circuit is the same also.
Alright guys, so here's an example of the Physics C math kind of part of circuits. This is a series circuit example. So here we see all circuits connected in one path. Series, essentially the definition of a series circuit. So here we have 3 resistors, each of 2,000 ohms, the case standing for 1,000, and so we can just fill out our table here to help us solve for the unknown variables with each of them. So 2,000 here, 2,000 for this one, and 2,000 for the next one. Alright, this gives us a grand total of 6,000 ohms, and we'll say this circuit has 12 volts, so we can actually fill that in for a total of 12 volts. And since we have both of these but don't know the current, we can actually use Ohm's law to help us find that. So Ohm's law is V equals IR, and if we plug in 12 and we plug in resistance of 6,000, we get a grand total of I equals 0.002. So we might be missing 0, but I think that's about right. So 0.002, which is very small. We plug it in here to get 0.002, and that is actually the current throughout the entire thing. This is a series circuit, and Kirchhoff's law shows that the current will be the same throughout. So 0.002, 0.002, 0.002 again. And then lastly, for voltage, drops in voltage, which V stands for at the top. Since we know that each resistor has the same amount of resistance of 2,000 ohms, and we know that according to Kirchhoff's other law, that the sum of all the drops in voltage must be equal to 0, we must know that there must be an equal drop in voltage with each resistor. So the total amount will be 12 divided by 3, so each will have a drop of 4 volts. And this is how you figure out unknown variables for a series circuit.
A parallel circuit is a closed circuit in which the current divides into 2 or more paths before recombining to complete the circuit. Each load connected into a separate path receives a full circuit voltage, and the total circuit current is equal to the sum of the individual branch currents. You use these in your house and stuff.
Here we have a similar example, but now concerned with a parallel circuit where we still have the 2,000 ohm resistors with 3 of them, and we'll make this also 12 volts. So we go back to our table here, we'll have 12 volts again, and we can't just assume that it's 6,000 this time for the total amount of resistance, since this is a parallel circuit. So parallel circuits actually have a special formula for finding the total amount of resistance. So if we go to it, it's 1 over the total amount of resistance, 1 over RT, T for total, equals 1 over R1 plus 1 over R2 plus 1 over how many ever resistors we have. In this case we have 3, so let's do 1 more. And if we plug it in, we'll get 1 over, actually, we'll just skip that, but it becomes 3 over 2,000 for the 3 resistors, each 1 over 2,000 added together. And this will equal 1 over RT. So if we cross multiply, we will get 3 RT equals 2,000, and that will give us RT of 667 ohms. So if we put it in 667 ohms. So if you actually notice, this is smaller than each of the resistors. So that is a key point when doing parallel circuits. So now we actually have voltage and resistance. We can find the current in the entire circuit. So we do the formula V equals IR. We plug in 12 and we plug in 667. And we get I equal to 0.018. And we put that there, 0.018. And since this is a parallel circuit, the current is not the same throughout. But since there is 3 resistors all of the same resistance, the current will be split 3 ways evenly. So this will be going to be 0.006, 0.006, and 0.006. So current stays the same. Then lastly, for voltage, since there are 3 independent paths, the voltage, drop in voltage will be the same throughout, and in this case it'll be 12 through all of them. So it'll be 12, 12, and 12. And lastly, for power, which is what the P stands for in this verb table, power is going to be equal to voltage times the current, because power is the change in energy over time. So if we just do this simple multiplication, it will be 0.072, 0.072, and then you get 0.072. This comes out to a total amount of power of 0.216, and that is our verb table.
So welcome on our journey
to circuits. I'm here. Deon is also here. George could not make it to Chuck E. Cheese because he was only 17. Sorry, George. Anyways, we're walking in Chuck E. Cheese. Just having fun out here. I can't switch it. Look at this example of circuits right here. 50 poppet bonus.
We are learning about circuits through Chuck E. Cheese.
Oh my gosh. Through our experiences at Chuck E. Cheese, we have found a lot about circuits. Circuits help us enjoy things like basketball and Deal or No Deal. I was going to explain to you circuits, but it's still not my turn on the Fast and Furious ride. Meanwhile, in the wilds, on a nice, fine Saturday afternoon, nowhere else I would rather be than Chuck E. Cheese with my boy Deon.
We're gonna race.
R.I.P. George. Yeah, we couldn't make it. Me and Deon are about to race. Should be a lot of fun. This is how you utilize circuits right here. Forget light bulbs. Just cars racing. That's where the real men are. So we're here at Deon. This is as if we turn on the circuit. Deon is now the flow of electrons is free. Deon climbs into the tunnel. Oh, he passes an electron. Oh, there is a resistor. As the resisting children symbolize resistors as there are in the current. Oh, we see a child and Deon stuck right there as he looks at us. We must rage to Deon. He's passing through the wire now. And this kid symbolizes a light bulb. Also from resistance. Oh, we have found Deon once again as he passed through the current. Oof. What a fine gentleman. Oh, love me that music. As Deon continues, oh, he's coming back around now. There's a bit of traffic. Deon is meanwhile driving on Chuck E. Cheese 95. Oh, he disappeared. He went other ways down the tunnel. Oh my gosh, look at Deon once again. Oh, and here is at the end of the circuit. Deon is traveling. Oh my gosh, look at him. That speed of 5 amps. Deon, what a pristine gentleman. As he goes down the slide. And he's having resistance against the friction of the slide, which I could explain, but does not relate to circuits. He's coming down the tunnel. Oh, it's Deon. Oh my gosh, why are you so young? What happened to you, Deon? Oh no, that's not Deon, just kidding. Oh, here we go, Virginia Tech strong. Boy. As we see here, circuits operate parts of our everyday life, including this token machine to buy new prizes at Chuck E. Cheese. You can see the lights and the small circuit boards right here going on.
I like to move it, move it. I like to move it, move it. I like to move it, move it. You like to move it, move it, move it, move it. Oh, he's snipping my sneakers. No, Jody's biting my hairs on my legs, dude. He's trying to brain blast so bad, but he can't. Oh, George! Oh my God! How's it going? Crocodile Dundee. Boy, he's screaming. Yo, we got the animal whisper right here. Yo. Oh. He's like, oh. Hey, George, put him back, and then I'll find something. Then we'll say something.
Okay, I'm gonna try. No.
You guys need some help?
I mean, yeah, a little bit.
Chuck! Get!
Oh, okay. That was fast.
I don't get paid enough for this job. Do it, man. Do it.
Voltage.